Ngā mihi nui kia koutou katoa. Ko te ahumairangi, te maunga. Ko te whanganui a tara, te moana. No ingarangi me kotarania me te iwi hurai o ku tipuna. Ko Timothy Goddard toku ingoa. No reira, tēnā koutou, tēnā koutou, tēnā koutou katoa. Hi everyone, I'm Tim Goddard and I work as a Principal Security Consultant at CyberCX. My background is in software development, so I worked for many years in a few different languages, most recently Ruby, building software. So about 7 years ago I shifted from software development into security, and I've carried through my software development background and experience into that by focusing on AppSec and secure code review and how we build software securely. I'd like to say thank you to all of the sponsors of this event. You've heard this a few times today, but genuinely without them we could not have nice things like conferences like this. So, let's imagine for a moment that you've been building a piece of software, a little app called DVWA, and your project had a pen test, and it came back looking something like this. You've got some executive summary that tells you everything is broken, and you've got a series of findings. So we've got a report. How do we deal with this? How do we work through this? The most common way that people will take to try to work through this is they'll open up their ticketing system, they'll create a ticket for each issue in that report. Maybe they'll even pick up a high-level recommendation or two and open tickets for them. But it's very much item-by-item tickets, and each one, click, will look something like this. Fix this bug. We got a report that we encountered this bug. Please, can one of the developers fix it? You copy in the details, you send it to the team, they work through the tickets, and all closed, all released to prod. We're done, right? Not quite. Penetration testing is not an exhaustive process. A good penetration tester goes through an application, they find all the functionality, they test everything they can see, they then go through all of the requests that were made and try to find ways in which they might cause the application to behave differently. This is often combined with automated scanning or fuzzing, which just throws a whole series of expressions in every field of every request and goes, did I see something weird? But there are a few reasons why this doesn't cover everything. For manual review, we have time limits, right? Penetration testers have a certain window of time in which to accomplish their testing, and there are only so many things that you can test by hand. So we tend to prioritize. We pick the areas of the application that from our experience are likely to have problems, and we focus our dedicated attention on those areas of the application. To get a better baseline, we use automated testing. We take all of the requests we made while interacting with the application normally, we throw those into an automated tool which makes those requests again for us, injecting content into each parameter. But this doesn't uncover all the bugs, because bugs don't necessarily occur when we make a change to one parameter of a request. There might be a setup step required. It might be that you have to make one request and then go and observe the results elsewhere, and the automated tool is actually overwriting its own attempts to inject something. For various reasons, testing by hand uncovers really complicated bugs, but testing in an automated way tends only to uncover the really simple cases. And we don't usually, in a pen test, have access to code. I do a lot of code reviews, that's not typical. We don't always have access to the code, we can't always find things that we don't observe while using the application normally. Now, I've been privileged over the years to work with a few customers who take security really seriously. And I'm not talking about taking security seriously in the same sense that everyone who's ever had a breach says they do. I'm talking about making significant steps in advance, dedicating significant effort to resolving bugs. To give you a picture of this, my most extreme example is I had a bug that only affected Internet Explorer, well past Internet Explorer's use-by date. I had a customer spend a month trying to fix this bug with a dedicated team, and that is how the most serious end of the spectrum are dealing with things. We don't have the resources to do that, right? We have to find relatively easy ways of fixing things. But the point is that these customers who take things really seriously don't actually think about fixing bugs. They think about fixing entire categories, entire classes of bugs, and stopping them coming back. So whenever you see a pen test report and you've got a list of issues, I'd like you to assume that that is not an exhaustive list. Every finding you see in there is an indication that in your application, in the way that you are building it, in the way that your developers are thinking about security, that type of bug can occur. So think about, is there more than one of these? Does this represent an ongoing pattern? Search for more instances and try to fix things in a consistent way. So, we're going to work through a finding. This is what a finding in a pen test report might look like, or at least the first, this much of it. There's probably a whole lot of rolled out reproduction steps underneath that, yeah? So, we've got a directory traversal bug. An attacker puts some content in a parameter, .. This is put into the middle of a file path and results in it going upper level, retrieve a file from some unintended location on the file system. We may have a series of limitations, so on and so forth. Doesn't matter. The point is that we've got a report of one bug and we've got an indication of how we might go about reproducing it. So, let's create a ticket for our developers and ask them to have a look at this more systematically. Let's ask our development team to have a look and understand genuinely what caused this vulnerability, find any other places where we might have made the same mistake, and fix it systematically through our whole code base. It's all very well me getting up here and telling you, go and do this, but how do you go about doing this? Now, I don't want to prescribe any one approach today, but I also don't want to leave you without a series of concrete kind of steps that you could take. So I'm going to have a discussion about how we might go through this. The first step is to reproduce the bug. It's always worth taking a bug, reproducing it, checking that you can actually make this happen under your test conditions, because it's a lot easier to work out what's going on if you can do this. In this case, we've taken the URL that was provided to us in the report, we've put it into a browser, and we can see what's going on. Up in the URL bar at the top of this page, we've got a security parameter. Maybe a little hard to read, but it's got .. in it. And we can actually see the file that's being loaded under the title there. It's vulnerabilities/exec/source/.. which is essentially undoing those directories and then saying, I want to load the config file. What we've got here is the config file for our app, which includes database credentials. So, we've reproduced the bug. Let's work through our code. Let's have a look at this and try to find the code which is responsible for this. We start with the endpoint, with the point that we identified that's receiving user input, and we work through our code base until we find where we think this bug is occurring. Now, I understand not everyone in this room will be comfortable reading code, but I promise you, we can work through this. Up the top there, you'll see two lines, ID equals $_get ID. That's retrieving the ID parameter from the URL, storing it under the name ID. Below it, we've got $security equals $_get security. Retrieve the security parameter from the URL and store it in security. And remember, this is the one that we had the injection in before. Down the bottom of this, we've got the line which is responsible for this bug. We've got file get contents, which does exactly what you would think. It takes a file name and it gives you back its content. And in the file name that we've got being passed to that, we have those ID and security parameters. So without any checks in the middle, that bit in the middle is just choosing what title to put on the page. Without any checks in the middle, we are taking user input and putting it into a file path. So, we found one instance. We know where this occurs, but we know now we're not just going to fix this one instance. How do we find the rest? The simplest way to go about this is just to start searching for keywords. We know that file get contents is where the actual bug occurred. It's a reasonably, it's not going to occur in every line of every file, so we search for it. This gives us back a series of vulnerable cases. It also gives us back a series of perfectly fine secure cases. So you now need someone with enough experience to go through that list of places and decide which ones are and aren't vulnerable. Mistakes will be made. It's not a terribly repeatable process. You can't do this for every change you make. An alternative to this might be to throw one of the big commercial static analysis, SAST scanners, at your codebase. Now, if you throw one of these scanners at your codebase and it comes back with that bug, why did you spend all that money on pen testing? But if it comes back with that bug, you can be reasonably confident that it will also come back with similar cases. But what if it doesn't come back with that bug? What if you've got something which is a bit of a niche issue, something that isn't quite as blatant as this, that doesn't appear in one of those commercial scanners? Most of these scanners, their value proposition is the vendor has created a big database of rules that match things that are insecure, yeah? You don't have to know all of this, you run the tool, it tells you what might be bad. But they don't tend to let you write your own rules. I'd like to introduce you today to one that does, to an engine called Semgrep. Now, I just want to reiterate before I go into this, the point of this talk is not to tell you to do things in one way or to tell you to use a particular tool. It's not a tutorial on that tool. The point is to show you that this is possible, that we can go through and find bugs systematically in our code base. Now, this tool, Semgrep, is short for semantic grep. It allows us to search for vulnerabilities, or really any pattern we like, in our code. The core tool is open source and available from their website. The project kind of funds itself by selling the enterprise add-ons that go with it. And unlike a textual search, it understands the structure of code. It doesn't care if your white space differs a little bit somewhere, it's still going to match. And our search patterns, helpfully, look a lot like code. There are alternatives that are a bit harder to use. This one's quite easy. So, we want to write a rule to match the bug that we saw before. Every rule that we write, you can see up the top here, there's rules and we've got kind of a list of things. This is a YAML file for those who are familiar with all of the advantages and disadvantages of that format. We've got an ID for our rule. We've got a message and severity, which will come out when this matches something and controls how it's reported. And we've got the languages we want to scan, in this case PHP. The engine supports a lot of different languages, some better than others, but a lot of different languages. I believe it's actually written in OCaml, so they're quite keen on having variety of options. Then we've got our pattern that we want to match. We can have one or more things that match, and in this case, we've just got the one. We've got this thing that looks kind of like the code that was vulnerable, but instead of being everything literal, we've got these ... these ellipsis marks in the middle, and that just means I don't care what goes here. So at the top there, we've got $var equals $_get ... I don't care what the parameter is called. The user can control it either way. In the middle, I've got a ... I don't care what code is intervening for the purposes of this match. And at the bottom, I've got file get contents, and that weird expression means some expression involving that variable. Now that $var thing, for those of you who do PHP development, will look a lot like a PHP variable. That's not. That is a Semgrep meta variable, which is basically a placeholder. And the constraint is that it has to be the same throughout the pattern. So how does this line up? How does this match our vulnerable code? Well, the $var equals get ... matches that first line of ID equals get ID. This binds var to be ID throughout the rest of our pattern, so that has to be consistent. We have a ... which swallows up everything in the middle. All of those lines in the middle get ignored for the purposes of this match. And then at the end, we ask it to match some expression including var, which is now bound to ID. So because we can see that file get contents thing at the bottom makes a reference to $ID, the thing that we bound that to, this matches, and this produces a result. We run it, and this is the command line version. For those of you who prefer something beautiful and graphical and so on and so forth, there are enterprise options for that. This is the command line version that we run with our rule, and it produces a series of outputs. We can see that this, if you look at the number at the bottom, has actually produced 8 findings. 8's a few more than 1. There's a little issue with this. What if our code looked like this instead? Instead of taking that user input, putting it directly into file get contents, I've actually constructed the file name as a separate line there. This wouldn't match anymore because it doesn't look enough like what we did. So the solution that Semgrep has for this is called taint mode. We say anything that comes out of a particular source is tainted or dangerous, and we see if there's a path by which that can end up in one of our vulnerable sinks. So in this case, I've rewritten the rule using taint mode, and our dangerous source is $_get, again, any parameter name, we don't care. And our dangerous sink is the file get contents call. Oh, and a key point for this is, please note, this does not actually run the code. It doesn't know which functions call which other functions at runtime. It doesn't understand conditional statements. All it does is read from top to bottom through the code and say, you've set this variable with an expression that contains another tainted input. Therefore, that's also tainted. Once we've done this, we know that the only place we can get user input is not that get query parameters. There are a bunch of other places in the HTTP request that we would retrieve in different ways. So in this case, we have post variables. Request is just kind of an alias for the first two stuck together. We've got cookies, something you might not be aware of. The attacker is in control of the cookies. They can set those to whatever they like. And we've got server, which in this case just holds all the HTTP headers. Yeah. So again, the attacker could set those. And we've got a bunch of other places that it could be dangerous to send this input as well, with roughly the same consequences. We've got the basic file function, and we've got this expression at the bottom for file put contents. I'm not going to go into a great degree of detail on that. Just trust me, that expression means I only care if it ends up in the first argument, because it's pretty common and pretty safe to read something from a request and write it as content into a file. As we expand our search parameters, there will be false positives. We will come up with things which should not be vulnerable. So in this case, we caught the reCAPTCHA library that's been incorporated into DVWA. It's not actually vulnerable. What's happening here is file get contents is actually being used to read a URL. Now, PHP has a virtual file system that makes this just work magically, but actually the user input is being safely URL encoded and put into that URL. It's fine. So we can add a series of sanitizers, and I use this term loosely in this case. We can add a series of expressions that says even if what you put into this is bad, the output is safe, and that's a sanitizer. URL encode is not, in general, a valid sanitizer for file names. Because this happens to be usable for URLs, and because it's a reasonable heuristic that we will only use URL encode for URLs, this is a decent heuristic in our code base. If we weren't comfortable with that assumption, we could make a different assumption. We could say, oh, you know, I want to match things from server, but actually exclude the things in the remote address field, because that one's fine. Once you've found the list of findings, fix them all. Go through, fix them all in a consistent way, and don't spend a huge amount of time proving that each one is vulnerable. If something is a dangerous pattern, it is worth a refactor to turn it into something safe. It can take you a lot more effort to prove that in this particular configuration this is vulnerable than it can take to rewrite your code in a form that is never vulnerable. So, you know, do this. Hopefully you have tests to check if it breaks anything. Once we've got this rule, deploy it in our pipeline. We've got a CI/CD pipeline, hopefully. Deploy this as a test, so that if someone reintroduces it, it comes back and warns us. And we rarely have one application, right? Lots of organizations will have a bunch of applications that are written in the same language and the same framework by some of the same developers. They're probably making similar mistakes. So reuse it for our other applications where that rule might apply. The final step in our journey to improve our security through this here is to switch from looking for the bad things to looking for the good things. Because as we know from attempting to block a million different variants of a script tag, trying to block bad things doesn't work very well in the long run. So let's have a think and go, okay, can we look for what we actually want to happen instead? And this is a game of choose your own standards. As a group of developers, you can choose a set of standards that you will voluntarily abide by. I, as a third-party tester, can't come in and prescribe you must build things in this way. That would be inappropriate. It's your choice. But as a development team, you can set down some fairly strict standards that you will follow. And then you can actually enforce these standards using Semgrep. I don't want to break down every line of this rule, but a common standard a team might have is that a SQL query we send to our database must be static strings, or must be built out of static strings. When we need to provide a user parameter, we don't feed that in as text in the SQL query, we feed that as in to the database backend for a placeholder. So here we've got, in the run-up to executing a query, look for adding something to the query, and then I've got an additional constraint on that meta variable. Remember I said that has to be consistent through the pattern. You can also add extra constraints to say it's not a fixed string. So it will pick up anything which is not a fixed string being added into a query. And this is a test case that I ran it against where it picks up me adding an ID parameter into a SQL query which is later executed. So the key messages that I'd like you to take away from today are not Semgrep is awesome, though Semgrep is awesome. The key message I'd like you to take away from today is that the really capable development shops are focusing on fixing bug classes, not individual bugs. Stopping those bug classes from recurring and making sure that they solve a problem now and for the future. For every instance of a bug that you get, whether that's through a pen test report, whether that's through a bug bounty program, or whether that's through your own internal security program, assume there could be a few more of them and have a look. Use the rules that you develop as part of this process to prevent the reintroduction of issues, right? We want to carry forward the benefit we achieved today into the future and not have the same problems occur again. And ideally, what your team should do is choose one safe standard, or two if you have a legacy one that's kind of okay, and enforce it through your code base. Say, tell me whenever I'm not following that standard, because that's something I really need to look into. I think rather than taking questions in person, the better approach today to enable everyone to participate is actually going to be to use the Hoover app. There is a per session Q&A in there, so please feel free to ask me questions in there. I will check in and answer them. Thank you everyone for coming to my talk.